minus 1 approximately.
Right.
And so we've got some kind of we might come to rest anywhere on this axis, and we need to figure out, is it only the origin or could it be some other point on that axis? So when we look for equilibrium points, we set x dot equal to 0, and we find that x is equal to -1, 0, or 1, right?
Okay, so I guess we don't need to do m dot equals 0.
Yeah, we could. It would technically be proper. I'm pretty sure the set that is invariant is going to be the equilibrium points, right? Because if you are off of those equilibrium points, x double dot's going to be non-zero, and so you're going to move off. So yeah, if you look for d by dt of x dot equals 0, this is x double dot equals 0. This is the proper, right? We've got x dot equals 0 is our definition of our candidate set. D by dt of that is x double dot equal to 0. This is our equilibrium points. I went there a slightly different direction, but if you did it due to finding m, that would be fine too. That's probably the technically proper way of phrasing it. Any other broad random questions people have? No? Everything is perfectly clear, or you want to keep your brain not fuzzed out in order to get questions 4 and 5? Just to check, is anyone posting desperately on Piazza saying, "Let me into the building"?
Nope.
Suck.
Nope.
Cool. No worries. All right, question 4, the one none of you did because no one knows what's going on, right? Let's briefly do concept level first then. I hope Brock did this already. We're again going to do a U1, U2, where U1 is going to cancel our plant dynamics, and U2 is going to give us our desired dynamics. Same setup as we've done a bunch, but now we're dealing with systems. I don't remember, I think it's of x plus g u. Something like that is the notation to start out with to match lecture, maybe? Right, this is extremely generic. We're just going to separate out our control, but now it can even be control multiplied by a function of the state and a function of the state to get us our time derivative.
Yeah, Rob usually writes the left thing as y to give us that output. It's input-output linearization, right?
We pick y equal to some state, or a combination of states. But
But I
this
think-
is our derivative part.
Yeah, I think in class you wrote it as y with some number n of derivatives on it
got it.
equals f of x plus g of x times u.
The nth derivative of y.
Yeah.
Yes, sure. Another way of saying that, I think it's going to be equivalent to this being x dot and then y being the nth derivative of x.
Yeah.
One of those is a scalar equation, one of those is a vector equation. There's a right way to do it. Point being, U1 is just going to be negative F over G, canceling out our dynamics, right? This is always. And if you're worried about what if g of x is 0, you're right, that's a problem. This method has problems. But when it works, it can work very well. So, u2 is, again, 1 over g, and then times our desired dynamics. Whatever those may be. Typically in any kind of problem we're going to give you, it'll be something like put all your poles at minus lambda. And so if we've got a second order system, it'll be y double dot is equal to y desired double dot. Actually, start from error double dot plus error dot lambda error, what, 2 lambda error dot plus lambda squared error equals 0. Second order error dynamics to put the poles root locus at double pole at minus lambda, right? Generalized version is s plus lambda to the n e equals 0, something like that. And then we're going to take the highest derivative term and break it apart. That this is y desired double dot minus y double dot. Because what we want to solve for is y double dot equal to thing, because we're going to be plugging it in where our y to the n, y-nth derivative is equal to our u. So to get these desired aerodynamics, we want to solve for y double dot equals. So I take all of this and make it U2. Goes in here.
Wouldn't it be the negative of, wouldn't it be like y double dot is y double dot desired minus 2 lambda e dot minus lambda squared?
I moved y to
Oh,
the
your
other
error
side.
is that way. It's desired minus actual.
Yes. And if you flipped order here, you would be flipping order inside your error definition as well. So it all works out either way as long as you are consistent.
Just the power, is that a power or superscript?
Nth derivative.
Nth derivative, okay, and then so it's the same thing up at s plus lambda n.
Yeah. No, this is s plus lambda to the n.
Yeah.
Because s to the n is the nth
Is it,
derivative.
okay.
I find it way easier to do this on specific derivatives rather than nth derivatives, which is why I worked this out on the second and then wrote down the general.
Okay.
Are you always just trying to match it?
Yeah, so if this is second derivative, second derivative. If this is fourth derivative, fourth derivative. What we are doing, and in principle, you can pick any error dynamics you want. Right, you could put one pole at minus lambda, one pole at minus 2 lambda, etc. You can put them anywhere you want. This is pole placement, but for nonlinear systems.
And sorry, that's s plus lambda to the what?
To the n.
The n. Oh, I thought that was.
So if this is the nth derivative, we are matching the nth derivative of our aerodynamics. But everybody remembers pole placement from 205, right? Right?
Ecker?
Yes. Good.
Mallet does most of the work.
But in concept, if you've got enough control authority, you can put your poles wherever you want. This is the same concept on a nonlinear system. I'm going to cancel out my dynamics, whatever they are. You know, if G is going very small, my U1 is going very large. That says my control authority has very little ability to move my plant, but I don't care, I'm going to push harder. And then my U2 is going to be whatever it has to be to make my system do what I told it to do.
Isn't that like a kind of waste?
It
It is a huge waste, right?
It depends. It might be. It offers no guarantee that it isn't. But if you've got tons of control authority, or your G2 is well behaved, it's never close to zero. It scales from, it might be constant, or it might scale from like 10,000 to 20,000. Okay, as long as we account for it, we can control through this system. And then I can get whatever aerodynamics I want. I really like exponential decay at this rate. That gets me there perfect. That gives me good enough tracking.
First world problem.
You're in a controls class. You're gonna deal with first world problems. Concepts in terms of this method that we haven't touched yet are if there are internal dynamics left over. So if there are dynamics besides those covered in y to the n, that's where I started writing x dot. Right, this is going to have potentially more states than the number of derivatives, than the derivative order of y. And so there can be internal dynamics to the system. And if those are unstable, you've got a big problem. Homework 8, you will see this. Just spoilers. In any event, let us get on to problem 4. This is actually a really cool physical system.
Do we need to understand the diagram? Or can we just like look at the
Technically,
equation?
no, but it's cool. Cylinder that is pivoting fixed, and another cylinder that is rolling on it. We are applying a torque to the lower cylinder, and we're balancing the upper one. Isn't that cool?
Like this? Like,
Yes, that is cool.
like
All right. What we actually care about is, what was it, x1 double dot is sine of x1, and x2 double dot is negative sine of x1, something like that, plus u.
Yeah, let's do.
And then we're told that we're going to do this input-output linearization feedback, what's the name of it?
Input-output linearization.
Input-output linearization 2 different times using 2 different choices of y. So y1 is going to be x1 and y2 is going to be x2, if I recall correctly. And those are x1 and x2, they're the angle of this lower cylinder, or the angle, this is one of them, and this is the other, right? This is y1, this is y2, right?
Yeah.
So we can either try to balance this cylinder just by moving it to the top, that's concept 1, drive that angle to 0, or drive the angle of the upper cylinder to 0. Does that make sense? The physical difference between the 2 control methods?
I can't, what's the inner way?
It's the angle of the upper cylinder
Relative, just ask.
relative to a reference.
Vertical.
Yeah, yeah, I mean, typical reference on this is gonna be set 0 as vertical. So, y1 is x1. First thing we do on these problems, differentiate until we get our control. y1 dot is x1 dot, y1 double dot is x1 double dot, which is sine x1 plus u. We found our control. We've gotten it into that form we need, which is nth derivative, in this case second. Derivative of y is, here's our f of x, and g of x is 1. Right? All we've done so far is pattern match to the setup we need for this problem. So for first controller, u1 is negative f, which is negative sine of x1. And u2, second order aerodynamics, and I think he says put the poles at minus lambda, is that right? You can either rederive, or you can just have in your notes, or you can memorize, totally up to you. The y desired double dot minus, sorry, plus 2 lambda error dot plus lambda squared error, that thing. You can either rederive or just remember it because you did it 2 seconds ago when you laid out the concept. But this, g is 1, so our u overall, u1 plus u2, which is minus sine x1 plus y desired double dot plus 2 lambda error dot plus lambda squared error. Does how we got here make sense? Cool. Let's talk about internal dynamics. So we need to figure out what x2 is going to do.
I have a question. So when we design this controller, we assume that y2 doesn't move at all, or?
No, we are choosing y equal to some state variable or derivative of state variable. And then we are going to drive that y to 0.
Right.
On dynamics that we are basically doing pole placement on.
That alone will only get x1 or y1 to 0, right? It won't.
Yes.
Okay.
Internal dynamics, which is all the other dynamics of the system not accounted for in driving y to 0. And we definitely need to check the stability of those. x2 double dot is sine of x1. Actually, orders. So y, we did 2 derivatives to get to u, and this is a 4th order system, right? 2 second derivatives. So this, we should expect to have 2nd order internal dynamics, just as a self-check kind of level. x2 double dot is 2nd order internal dynamics, so we don't need to go searching for anything else. x1 is y1, which we're going to drive to 0. So when we look at our internal dynamics, we've got x2 double dot in the long term. x2 double dot equals 0, which means x2 dot is constant, which means x2 is increasing linearly, right? long term, we're driving y1 to 0 with our dynamics, with our control. Means we're driving x2 double dot to 0. But it will have been non-zero for some time before then. So x2 dot, let's see, x2 double dot goes to 0, x2 dot goes to constant, x2 of t goes to constant times time, right? Just for fun, physically what this means is we've spun the lower wheel to get the upper wheel above it, and now it's spinning at a constant rate, holding the upper wheel in place, but if you ever stopped the lower wheel, the upper wheel would then roll off. So you have to keep it spinning at a constant rate to keep it up on top.
What's x1 and x2 again?
X1 is, the angle is this angle here, the angle from center to center, and x2 is the angle of the upper cylinder.
So same as y.
Yeah.
So both of them are just continuously rotating.
Yeah, so in order to keep it sitting on top, we can do that, but we have to keep turning it forever. Rock looked at that and said, this is terrible. I looked at that and said, it's situational, right? This is unstable in the system blows up sense, but it's a cylinder. Cylinders roll forever without any problems, which is why I said it depends. Do you need it to come to rest, or are you okay with it sitting there spinning forever? The official answer, though, was that this is unstable and we don't like unstable dynamics.
It's unstable because it's linearly increasing, so.
It's unstable and sensibly Lyapunov.
Can you elaborate on that?
Stable in the sense of Lyapunov means
Yeah.
I can place a ball that the system doesn't go outside.
Okay,
There is no ball you can place.
okay, yeah. Okay.
So, again, Rock said unstable in the sense of Lyapunov. This is bad. I said it's a cylinder. Cylinders roll forever. They're fine with it. It depends. I graded this question. People didn't get points off for that. If Rock had graded this question, they would have. Rather, people didn't get points off for that if they explained that it was unstable, but that's okay because it's a cylinder and cylinders roll.
I'm confused. So like the acceleration of internal dynamics, which is just the ball angle at the top, is 0 there, right?
In the long term, this is all in the long term. x2 double dot, because we're driving y to 0 with these dynamics, x1 will go to 0, sine of x1 will be 0, so x2 double dot will ultimately be 0 with this control input. Therefore, x2 dot will go to a constant, and so x2 will be growing linearly with time.
So that is internal dynamics?
Yeah, it's internal dynamics because it's not seen in our output y.
So when we were asked to find, I'm not sure whether I'm not really seeing it because I haven't done homework or whether this problem is esoteric, but when we were asked to find internal dynamics of the system, are we expected to find something like, oh, x2 dot is 0, like is that sufficient? Or like, what
The
if-
internal dynamics are this.
which was just like straight up given to me.
Yes.
And that is, oh,
So if y had been set at x2 dot, or no, there's no good way to do it on this one. Do the homework. You'll do the question where I think it's like x1 dot is negative x2 cubed plus u, something like that, and x2 dot is negative u. It's something like that. Homework question. Now when you set U1 equal to X1, it's first order, there's internal dynamics. And when you set U1 equal to X2, it's again first order, and there's internal dynamics. Did that clarify anything or just make it worse?
But I don't, yeah. I will table that thought.
I would say poke at that homework problem and what we're doing here will make more
I
sense.
hope
Dave, can you say why we're, like intuitively, why are we driving y1 to 0? Because when I look at it, like we're setting up aerodynamics, so like in my head I'm thinking like, why aren't we driving the error of y1 to 0? That's what
Yeah, we are.
Okay, so we're not
But,
driving one.
so the setup on this problem said we are doing a regulator. Welcome back. We're doing a regulator, so we're
Yeah.
driving the system to 0.
Yeah.
That's a 0 input.
So we're actually driving the error of y1.